Burj Khalifa, the $1.5 billion engineering secret nobody could solve. September 2003. A massive crack splits the desert floor beneath what engineers insist is solid ground. The foundation of what will become the tallest structure ever built by human hands has just shifted. No one is supposed to know. One miscalculation, and the entire project dies before a single floor rises above the sand. Billions of dollars, years of ambition, and a secret so catastrophic, the construction team buried it inside classified reports that were never meant to be read by the public. Most people think the Burj Khalifa is a triumph of modern engineering. They are wrong. It is a monument built on the edge of collapse. A story of catastrophic failure, hidden panic, midnight decisions, and one impossible problem after another that nearly ended everything before it began. This is not the story they tell on the observation deck. This is the story buried in the ground beneath it. To understand why the Burj Khalifa nearly failed, you have to understand the world it was born into. Dubai in 2004 was a city already intoxicated by its own ambition. For decades, it had been a modest trading port on the Persian Gulf, a place of pearl divers, dhow boats, and desert merchants. Then oil arrived. Then the oil began to run out, and Sheikh Mohammed bin Rashid Al Maktoum looked at what remained and made a decision that would define the 21st century skyline. If Dubai could not survive on oil, it would survive on spectacle. The plan was simple in its audacity and terrifying in its execution. Build the tallest building in the world. Not by a small margin, not by a few floors. Build it so tall that every previous record would look like a footnote. 828 meters, 163 floors. A spire so high that the building experiences two sunsets on the same day, one at ground level and one visible from the upper floors after the ground has already gone dark. The project was assigned to Emaar Properties, Dubai's most powerful real estate developer. The design went to Skidmore, Owings and Merrill, the Chicago firm that had already built some of the tallest structures on Earth. They had designed the Sears Tower. They understood height. They understood wind, steel, and concrete at extreme altitudes. What they did not yet understand, what no one fully understood, was what happens when you push all of those forces simultaneously to a scale that had never been attempted before. The budget was set at $1.5 billion. The timeline was 5 years. And the problems began before the first shovel broke the desert surface. The soil beneath downtown Dubai is a geological trap. On the surface, it looks like ordinary sand. Pack it, grade it, and it holds the weight of roads, foundations, and low-rise buildings without complaint. But go deeper, past 10 meters, past 20, past 30, and the composition changes into something far more dangerous. The deeper sediment layers beneath Dubai are saturated with sulfate-rich groundwater. The sulfates come from the evaporation cycles of the Persian Gulf over millions of years, leaving mineral concentrations in the soil that act like a slow chemical weapon against construction materials. Standard Portland cement, the concrete used in virtually every building on Earth, reacts with sulfate compounds in a process called sulfate attack. The concrete expands. It cracks from the inside. Over decades, it crumbles. At shallow depths, this is manageable. Engineers have dealt with sulfate-rich soils in coastal environments for over a century. You use different concrete mixes, apply protective coatings, add drainage systems. But the Burj Khalifa's foundation would need to go 50 meters deep. At 50 meters, the sulfate concentration was off the charts of anything engineers had previously encountered in a construction context. And the foundation would not just touch this water. It would be permanently submerged in it forever. The lead structural engineer, Adrian Smith, and his team ran the numbers 3 separate times. Each time, the result was the same. Standard concrete, even high-performance concrete, would begin to degrade within decades. A building designed to stand for centuries would begin failing in its foundation within a human lifetime. They brought in chemists. They brought in materials scientists. They assembled a team that had never been assembled before for a construction project. And they gave them a deadline that no research project had ever been given. Solve this problem in months, not years, because the construction schedule cannot move. What emerged from those pressure cooker months of research was a concrete formula, unlike anything used in civil engineering before that point. The mix incorporated ground granulated blast furnace slag, a byproduct of steel manufacturing that had previously been considered industrial waste. It added silica fume, an ultrafine powder produced during silicon metal production. It introduced a carefully calibrated blend of chemical admixtures designed to reduce the concrete's permeability to near zero. The resulting concrete was so dense that water and sulfate ions could barely penetrate its surface. It was, for practical purposes, chemically inert in the Dubai subsoil environment. It would not react. It would not crack. It would not crumble. But there was a second problem layered on top of the first, and this one almost stopped the project entirely. Concrete generates heat when it cures. This is basic chemistry. The hydration reaction between cement and water releases thermal energy. In small pores, the heat dissipates quickly and causes no structural problems. In large pores, the heat builds up in the center of the mass, creating a temperature differential between the interior and the exterior of the concrete. That differential causes the concrete to crack as the outer layers cool faster than the inner core. The Burj Khalifa's foundation raft, the massive concrete base that would distribute the building's weight across all 194 piles, was nearly 4 meters thick and spanned an area larger than a football field. Pouring this quantity of concrete in Dubai's summer heat would generate internal temperatures exceeding 90 degrees Celsius. The concrete would crack before it even finished setting. The engineers had two options. They could pour the foundation in winter when ambient temperatures are lower, but the construction schedule did not allow for a 6-month delay, or they could cool the concrete itself. What followed was one of the most unusual industrial operations in construction history. The team set up dedicated chilling plants on site that cooled the mixing water to near freezing temperatures before it entered the concrete batch. They replaced portions of the mixing water with crushed ice manufactured on site in industrial quantities and fed directly into the mixing drums. They used liquid nitrogen to cool the aggregate, the gravel and sand that make up the bulk of the concrete mix, before it was loaded, and they poured only at night. For 4 consecutive days and nights, an unbroken convoy of concrete trucks rolled onto the Burj Khalifa construction site. At peak flow, a fully loaded mixer arrived every 30 seconds. The pumps ran continuously. The temperature monitoring teams worked in rotating shifts, measuring the heat of the pour at dozens of points simultaneously, adjusting the ice ratios in real time based on the readings. If a single section of the raft had been allowed to begin curing before the adjacent section was poured, a construction joint would have formed, a plane of weakness running through the foundation that could, under the building's eventual load, become a fracture point. The entire pour had to be continuous. The entire pour had to be cold. And the entire pour had to be completed before the desert sun rose high enough to overwhelm the chilling system. They succeeded by a margin that the project engineers later described in private as uncomfortably narrow. The foundation raft was complete. The piles were driven. The base of the world's tallest building was in the ground. And no one outside the construction team knew how close it had come to catastrophe. The building began to rise. In the early floors, the pace was almost ordinary. The core walls went up, the floor plates extended outward. The distinctive Y-shaped floor plan, 3 wings radiating from a central hexagonal core, began to take visible form as the structure climbed through the first 100 meters. At this stage, the Y-shape looked like an architectural choice, something elegant, something designed to maximize views from the residential units that would occupy the lower floors and the hotel that would fill the bottom quarter of the building. It was not an architectural choice. It was a structural survival strategy, and the story of why it exists goes back to a wind tunnel test that genuinely frightened the engineers who ran it. When Skidmore, Owings, and Merrill began modeling the aerodynamic behavior of a building at 800 meters, the initial designs were conventional, a tapering rectangular tower with setbacks at regular intervals. Standard practice for super tall buildings. Proven geometry, known behavior. The wind tunnel results for those early designs were catastrophic. At the heights the Burj Khalifa would reach, a rectangular or near-rectangular cross-section creates a phenomenon called vortex-induced vibration. As wind flows past a bluff body, an object that interrupts rather than guides airflow, it separates from the surface and forms spinning vortices on the downstream side. These vortices shed alternately from each side of the building, creating a repeating lateral force that pushes the structure back and forth. At low amplitudes, this is manageable. Buildings move. That is acceptable and expected. But vortex shedding becomes catastrophic when the frequency of the vortex formation matches the natural resonant frequency of the building itself. At that point, each oscillation adds energy to the next. The building begins to amplify the wind's input rather than dissipate it. Engineers call this lock-in. Structures that reach lock-in have failed. Bridges, chimneys, offshore platforms. The Tacoma Narrows Bridge, which tore itself apart in a 42-mile-per-hour wind in 1940, is the most famous example of resonance-induced structural failure. For a building of 828 meters, lock-in was not a theoretical risk. It was a near certainty with conventional geometry. The solution required thinking about the building not as a static object that the wind pushes against, but as a dynamic shape that actively disrupts the wind as it passes. The Y-shaped cross-section was the key. Each of the three wings of the Y presents a different face to the wind depending on wind direction. As the building rises and the floor plan gradually rotates, each tier stepping slightly relative to the one below, the cross-section the wind encounters is never the same at two different heights simultaneously. Vortices form, but they cannot lock in. The geometry changes before the resonant frequency can establish itself. The wind's energy is scattered across dozens of different frequencies rather than concentrating in one. The building moves, but it never amplifies. Over a period of more than 2 years, the aerodynamics team tested more than 40 distinct variations of the tower geometry in wind tunnels located in the United States and Canada. They tested different rotation rates, different wing proportions, different setback profiles. The final design emerged from that exhaustive process as the geometry that produced the lowest vortex-induced forces across the full range of wind speeds and directions expected in Dubai. The beauty of the spiraling silhouette that has become one of the most recognizable shapes in modern architecture exists because it was the geometry least likely to be destroyed by the air. By the time the building reached 300 meters, a new crisis was developing inside the construction management offices. The concrete pump was dying. Standard tower cranes and concrete pumping systems are designed for buildings that reach, at the extreme upper limit of their capacity, perhaps 250 meters. The pump forces liquid concrete through rigid steel pipes running up through the building's core, relying on hydraulic pressure to push the mix against gravity to the floor being constructed. At 300 meters, the pressure required to push concrete upward through the pipe was already approaching the rated maximum of the most powerful pump the contractor could source. At 400 meters, that maximum would be exceeded. At 500 meters, the pipe itself would fail. The project had reached a fundamental materials limit. The strongest concrete pump available on the commercial market was not strong enough to build the building being constructed above it. The contractor, Samsung C&T of South Korea, approached pump manufacturers with a specification that had no precedent. A pump capable of sustaining continuous pressure at levels previously seen only in offshore oil extraction equipment. The resulting machines were custom engineered from scratch, incorporating hydraulic systems, valve designs, and pipe specifications that had never been combined in a construction pump before. The pipes themselves required redesign. Standard concrete pump pipes are joined with clamp couplings designed to handle moderate pressures. At the pressures now required, those couplings would blow apart. The team switched to pipe sections with threaded joints, the same connection technology used in high-pressure hydraulic systems, and tested every joint in the system before each pour, and still it was not enough. On the day the construction team attempted to pump concrete to a floor above 600 meters for the first time, a pipe joint failed near the 400-meter level. The failure was explosive. The coupling blew outward under the accumulated pressure, and a column of liquid concrete, gray, heavy, and moving at high velocity, erupted from the pipe and began falling down the outside of the building. Workers on lower floors scattered. The construction halted. And for 6 days, the tallest building under construction in human history sat silent while engineers tore apart the pumping system, rebuilt every joint to a higher specification, and recalculated the pressure profiles for every remaining floor of the pour schedule. When the pumps restarted, they worked. But the 6-day shutdown had cost the project time it could not easily recover. And the memory of that explosion lived in the risk calculations for every subsequent pour, all the way to the top. The building passed 400 meters, 500, 600. The workers who built those floors never saw the street clearly from where they stood. Looking down from the construction platform at those heights, the cars below were invisible. The roads were geometric lines, the city was a map. Working at extreme altitude creates physiological effects that construction planners had not fully anticipated. The wind is different, not stronger necessarily, but more constant. There are no lulls at 600 meters, no sheltering effects from adjacent structures. The wind presses continuously, and workers exposed to it for extended shifts experience fatigue at a rate faster than ground-level labor. The heat is paradoxically more intense. At altitude, there is less particulate matter in the air to scatter solar radiation, and the reflective surfaces of the building's glass and steel amplify the direct sunlight hitting the work platforms. Core body temperatures among the workforce rose to levels that required mandatory cooling breaks every 45 minutes during daylight hours. The crane operators faced the most extreme conditions of all. The tower cranes that lifted materials to the upper construction levels were themselves taller than most completed buildings. Their operators worked in sealed cabs at altitudes where the horizon curved visibly. A shift at the top of a Burj Khalifa tower crane lasted 8 hours. The operators ate their meals in the cab. Bathroom facilities were a bucket. And the crane swayed, constantly, perceptibly in ways that took weeks to become accustomed to, and that some operators never fully accepted. Over 12,000 workers were employed on the Burj Khalifa at peak construction. The majority had traveled from India, Pakistan, Bangladesh, and the Philippines, and their wages were between $4 and $8 per day, an amount that represented, in many cases, more than they could earn in a month in their home countries, but a fraction of what the project's architects and engineers were paid. They lived in Sonapur, a labor camp on the outskirts of Dubai that housed over 150,000 migrant workers during the construction boom years. The camp had dormitories designed for 8 people that regularly housed 12. It had canteens, medical clinics, and cricket fields. It was, by the standards of migrant labor housing in the Gulf region, considered relatively acceptable. It was also completely invisible from the observation deck of the building they had built. The building reached 700 meters, 800. The spire began to take shape above the last occupied floor, and then the engineers encountered a problem that had no precedent anywhere in the construction literature, because no building had ever been tall enough to make it relevant. Water pressure. In a building of ordinary height, municipal water pressure is sufficient to push water from the ground floor supply connection to the upper floors. In a super tall building, booster pumps are added at intermediate levels to maintain pressure as height increases. This is standard practice, well understood. But at 800 meters, the column of water in the pipes from the ground to the upper floors creates a static pressure at the base of the system that exceeds the pressure rating of standard plumbing components. The pipes at the lower levels would burst, not from the pump pressure pushing water up, but from the sheer weight of the water column pressing down. The Burj Khalifa's plumbing system required a complete redesign of the pressure zone concept. The building was divided into pressure zones, sections served by isolated water supply systems with their own booster pumps and pressure relief mechanisms. Water moves through the building not in a single continuous column, but in a series of managed handoffs between zones, each one isolated from the pressures generated by the zones above and below it. The same zoning principle applied to the elevator system, though for entirely different reasons. A conventional elevator cable long enough to span even half the height of the Burj Khalifa would weigh several tons. A cable of that mass swings. It oscillates inside the shaft with a natural frequency determined by its length and the speed at which the elevator travels. At certain combinations of cable length and speed, the cable reaches resonance, amplifying its oscillations until it strikes the shaft walls repeatedly, eventually failing. The solution was to eliminate long cables entirely. The Burj Khalifa uses a sky lobby transfer system in which no elevator travels more than a fraction of the building's total height. Passengers traveling to the upper floors board a double-deck high-speed elevator at the ground level, ride it to a sky lobby at approximately the midpoint of the building, and transfer to a second elevator for the upper portion of the journey. The cables are always short enough to remain below the resonance threshold. The physics problem disappears because the geometry that creates it is never allowed to form. The result, from a passenger's perspective, is a mild inconvenience: 2 elevator rides instead of 1. From an engineering perspective, it is the only reason you can reach the upper floors at all. On the 4th of January 2010, the Burj Khalifa opened. The ceremony was unlike anything Dubai had staged before, and Dubai had staged extraordinary ceremonies. Fireworks launched from every floor of the building simultaneously, creating a vertical column of light that was visible from 60 kilometers away. The world's media gathered at the base. Dignitaries arrived from across the Gulf and beyond. And then Sheikh Mohammed stood before the microphone and said the name that no one had expected. Throughout its construction, the tower had been known as Burj Dubai, the Dubai Tower, a monument to the emirate that had conceived it and built it and nearly been bankrupted by it, because by 2009, the global financial crisis had hit Dubai with devastating force, and the emirate had required an emergency bailout of $10 billion from its neighbor Abu Dhabi to avoid defaulting on its debts. In recognition of that support, and in honor of the man who had provided it, Sheikh Mohammed renamed the building. Not Burj Dubai, not after any architect or engineer or developer, after Khalifa bin Zayed Al Nahyan, the ruler of Abu Dhabi. The tallest building in the world carries the name of the man who saved the project from financial collapse in its final year. Without that $10 billion, the Burj Khalifa might have stood half-finished above the Dubai skyline for years, a monument to overreach rather than triumph. The name is not incidental. It is the hidden financial story written in stone and glass 800 meters above the desert. There is one final secret about the Burj Khalifa that its promotional materials do not mention. The building has no connection to Dubai's municipal sewage system. When the Burj Khalifa was constructed, Dubai's wastewater infrastructure had not been designed to handle the volume that a fully occupied tower of this size would produce. The pipe network simply did not extend to the site with sufficient capacity. And rather than delay the opening while the city built the necessary infrastructure, a process that would have taken years, the decision was made to open the building and manage the waste differently. Every day, a fleet of tanker trucks arrives at the base of the world's tallest building. They connect to the building's waste collection points in the basement levels. They pump out what the building has produced, and they drive it to treatment facilities on the outskirts of the city. The most technologically sophisticated building ever constructed, a structure that solved problems in soil chemistry, aerodynamics, concrete physics, hydraulic engineering, and cable mechanics that had never been solved before, disposes of its sewage in trucks. The engineering that reached 828 meters into the sky could not solve the infrastructure gap at ground level. The trucks still come every day. The Burj Khalifa has been the tallest building in the world for 15 years. In that time, no other structure has come close to surpassing it. The Kingdom Tower in Jeddah, Saudi Arabia, was designed to reach 1,000 meters and began construction in 2013. As of today, it remains unfinished, halted by a combination of funding problems, engineering complications in the soft alluvial soil of the Jeddah coastline, and the same fundamental question that plagued the Burj Khalifa from the beginning: the ground beneath it. The Burj Khalifa's record appears secure for at least another decade, perhaps longer. What its record actually represents is not simply height. It is the outer boundary of what human engineering currently understands well enough to execute reliably. The problems it solved, the sulfate-resistant foundation, the aerodynamic geometry, the high-pressure concrete pumping, the zoned plumbing, the sky lobby elevator system, were solved under deadline pressure by teams working at the frontier of their disciplines with incomplete information and no precedent to guide them. Some of those solutions worked better than expected. Some worked exactly as designed, and some introduced new questions that have not yet been fully answered. The building sways. At the top, in high winds, the structure moves approximately 1.5 meters in each direction. This is intentional. It is designed. A building that cannot flex will crack. But at 828 meters, 1.5 meters of lateral movement generates measurable velocity differences between the top and bottom of the structure. And velocity, according to the physics of special relativity, affects the passage of time. The top of the Burj Khalifa, moving faster relative to a fixed external reference point than the base, experiences time at a marginally slower rate. The difference is measured in fractions of microseconds per year. This is not a structural problem. It is a measurement problem. The building's health monitoring systems, the networks of sensors that detect stress, deformation, and movement throughout the structure, use synchronized timing to correlate readings from different points in the building. At the precision levels required for structural monitoring of a building this tall, the relativistic time difference between the top and bottom of the structure is not entirely negligible in the calculations. The engineering teams have modeled this effect. The models suggest it is manageable at current sensor precision levels, but it has never been empirically verified with instruments installed in an operating building at this height. No such instruments exist. The Burj Khalifa is, in a precise and measurable physical sense, slightly out of time with itself. And no one knows exactly what that means over the centuries the building is designed to stand. On a clear day in Dubai, you can see the Burj Khalifa from 50 kilometers away. From the highway approaching the city, it appears alone on the horizon, a needle so thin at that distance that it seems impossible it could be solid, impossible that it could be real. It rises from a ground that wanted to swallow it. It was shaped by wind tunnels to confuse the air that wanted to shake it apart. Its concrete was invented in a research camp to resist the water that wanted to dissolve it from below. Its pipes were engineered to survive pressures that no construction pump had previously generated. Its elevators were divided to avoid the physics that would otherwise make them fail. It stands on a foundation poured in darkness over 4 consecutive days. It was renamed after the man who saved it from bankruptcy. It empties its waste into trucks every morning before the tourists arrive. It is the most ambitious object human beings have ever completed, and every engineering solution hidden inside it, every improvisation, every midnight calculation, every crisis that was solved and buried in a classified report, is a monument not to the limits of human ambition, but to the absolute refusal to let those limits be the end of the story. The secret was never the building. The secret was the people who refused to stop building it.